Section 3.1 talks about vectors in 2 dimensions and 3 dimensions and n dimensions. So if you're taking third semester calculus, this is a review. If not, here it is. So when we talk about, let's start with 2 dimensions. If we want to talk about vector addition, consider a vector w and a vector v. If I take vector v and I copy it right there, and take vector w and copy it right there, I'll create a parallelogram. The diagonal is called the resultant force. This is v, this is w. I would say this vector right here, the resultant, is w plus v, assuming you started this way, then this way. Or I could call it v plus w, it doesn't matter. So vectors, you want to think of vectors as moving belts. If I drop an item right here, I had one belt, drop it off here. Wherever this belt drops, this is called the tip. So base to tip. This vector picks it up and drops it off here. The resultant is always, if I was to figure out where did I drop it and which direct path can I take to pick it up, then that will work. This is v plus w, and this is v plus w. You could think of it 2 ways. Now, you don't have to draw the actual parallelogram, but it helps you to draw the parallelogram if you want to see the resultant. Now, a vector possesses both direction and magnitude. When we want to add vectors, now we're looking at those graphically. If this is vector v, you start where the base to the tip, w is right there. If you want to add those, you want to take one vector and move it, or the other, it doesn't matter. But if I want to take minus v, if v is moving, let's say 3 units to the right, minus v would be reversing the order. So you would run 3 units to the left. And if you want to take w minus v, this is w, this is minus v, well, you do the same. You say, look, this is w, this is minus v, and there's that parallelogram, that'll be v minus w. Now, we want to start with figuring out formulas. We're going to do this algebraically, not graphically. No, not geometrically. If we take the origin to be 0, 0, and vector 1 happens to, a point P happen to be at x1, y1, OP will simply be end minus beginning. OP1 will simply be x1 minus 0, y1 minus 0. If I look at another point, let's say that point, P2, then OP2 will simply be x2 minus 0, end minus beginning, y2 minus 0. If I take 2 vectors and I subtract them, then I'm going to subtract, I'm going from OP2 to OP1. So we're subtracting this vector from this vector. Then you simply take the components and you subtract them. You take x2 minus x1, end minus beginning, it's right there, and y2 minus y1. And that will be running from P1 to P2 in that specific direction, and that is P1, P2. If you have 3 dimensions, you just add the z component. Now, I could call this vector v. I could call this vector AB. AB is normally better, it tells you where you start and where you terminate. Now, if n is a positive integer, then an ordered n tuple is a sequence of n real numbers, v1, v2, all the way to v sub n. The set of all ordered n tuples is called the real n space and denoted by r sub n. Now, if I take vector v and it consists of the following components, w consists of the following components, they're both in Rn. If you say they are equal, then you're saying that the components must match. So it's kind of like what we did with matrices. Remember, matrices are a list of vectors. If you multiply a vector by a constant, they call it scalar, then you multiply each component by that scalar. If W is a vector in Rn, then W is said to be a linear combination, a massive topic for us, of vectors v1 all the way through vr, if it can be expressed as W is k1 times v1, k2 times v2, where all of these are scalars. In other words, if I could find a multiple of these vectors added or subtracted to get W, we say W is a linear combination of these vectors. Linear combination is a big deal for us. It's something we're going to be doing for a while, but that's going to come a bit later. These scalars are called coefficients of the linear combination. In our case, in the case where r equal 1 and 14, you're dealing with W equal k1 v1 only. So that a linear combination of a single vector is just a scalar multiple of that vector. Now let's get a few things going. Oops, how did that happen? A vector possesses both direction and magnitude. Now I'm assuming you know that. For some reason it just hit me right now. Maybe you don't know that. I want to review that a bit. You could move a vector anywhere you want as long as you maintain its magnitude, its length, and the angle it possesses that was given. Now we want to take vectors and we want to write them using component form. Now the book is going to write this slightly different than the way I'm going to write it. You always take end minus beginning. Notice the arrow. The arrow indicates you're running in that direction. So this vector right here, if I want to write it in component form, it's always end minus beginning. -3 minus 2, that's the I component, and 3 minus 3. So this vector is actually -5, 0. So this is what this vector does. Anything you drop at its base, it's going to move 5 units west. Now the book is going to write it like this. Again, you could write it that way. That's really -5a plus 0j, or just -5a. But I'm going to write it like this using the old traditional component form. And if I want to write this vector in 3D again, you're running in this direction. So what this means, if I actually do this, take end minus beginning, what we're doing, we're standardizing the vector, meaning we're saying if you start at the origin, all what this vector does is shift whatever item you drop on its base 5 units to the left. That's all there is to it. So pretty much I picked that vector and I just moved it right there. That's what this does. And if I want this vector, I'll simply take end minus beginning, 0 minus 3, 4 minus 0, and 4 minus 4. So this vector, pretty much whatever you drop at its base, shifts it 3 units in the negative x direction, 4 units in the y direction, and 0 units in the z direction. And here we go. If we want to find the vector going from P1 to P2, well, that's fairly simple. P1, P2 would be -4 minus 6 and -1 minus 2. That would be -10, -3. And if you plot this, you could pretty much figure it out just by looking at it. It's not that bad. Oh man, it's -4. I was just thinking that only moved 2 units. -4 minus a -2, that's That's just 2. And if I get to B, if I want to go P1 to P2, this is in R4. This is 3 dimensions, I'm sorry, R3. Negative 1 minus 0, 6 minus 0, and 1 minus 0. And there it is. Again, the book's going to write that this way. It's going to look more like a point. You could do that if you wish. Now, here we want to find the initial point of a vector that's equivalent. Two vectors are equivalent if they possess the same direction and the same magnitude. Equivalent to this vector u, which is 1, 2, whose terminal point is 2, 0. You could use common sense if you want, but I want to use a formula to make sure that we figure this out if the problem is not this simple. Let's say A happened to be the actual point and A has x1, y1. It's saying this is the terminal point, which means AB, they ran from A to B. Now, isn't that really, if I'm running from A to B, wouldn't that be 2 minus x1 and 0 minus y1? So that's pretty much 2 minus x1 negative y1, right? And you want it to be equivalent, identical to u. So if it's equivalent to u, you're really trying to set that equal to 1, 2. You want it to move 1 unit to the right, 2 units up, or 1 unit east, 2 units north. Well, what does that mean? That means 2 minus x1 must be 1. That means x1 must be 1. And you want negative y1 to be 2, which means y1 should be negative 2. So A should be the point 1, negative 2. That will mean those two vectors are equivalent. They basically do the same thing. Whatever you drop at their base. So here, really quick, if I start at 1, negative 2 and go 1, 2, 0, this vector moves an item that it dropped at its base 1 unit to the right, 2 units up, and this vector does the same thing, except that one starts at the origin and moves 1 to the right and 2 up. That's vector u. So I'm not sure how familiar are you with vectors, but we're gonna pretty much go over everything that's needed. Let's say we have 3 of those, 3 components, 3 dimensions. Find the terminal point of a vector. Now they're saying this is the initial point. The terminal point, call that x1, y1, z1, or you could just call it x2, y2, z, or just yz. Well, isn't AB, in this case, x1 minus 0, y1 minus 2, and z1 minus 0, and you want that to equal to 1, 1, 3, because those are equivalent. That means x1 equal 1, y1 equals, so y1 minus 2 equal 1, y1 equal 3, and z1 equal 3. So we say, look, the point B has to be 1, 3, 3. And those two vectors will be equivalent. Now, okay, looking at the next problem, find the terminal point Q. So this vector u is PQ, and they gave us P. So let Q be x, y, z. You could call them x sub 1, y sub 1, c sub 1, a, b, c, whatever you like. Then this PQ will simply be x minus a negative 1, y minus 3, and z minus a negative 5. Now, here they say, this is u. They say, with the initial touch that u has the same direction as v. Now, again, if two vectors have the same direction, that means they're multiple of each other. That means u is some multiple, like kv, where k could be any number, 1, 2, 3, 4. So pretty much we're saying x plus 1, y minus 3, and z plus 5 must equal some k times 6, 7, and negative 3, depending on what you want k to be. If we choose the simplest form, say k equal 1, for example. Then we're going to say x plus 1 equals 6. That means x must be a 5. Y minus 3 must equal a 7. So y must be a 10. And z plus 5 must be a negative 3. That means z is a negative 8. And therefore, we could figure out that the point Q is actually 5, 10, negative 8. Oh, that's what I meant. And if u has the opposite direction, the opposite of vector v is negative v. That's simple, or any multiple of that. Let's choose it to be negative 1 just to make it simple. Again, it could be negative 2v, negative 3v, and all what would happen here, well, it's the same work, so to speak. U is the opposite. U is oppositely directed from v. Well, in this case, we're going to take u equal negative v or v equal negative u. It doesn't really matter. So now if I take this vector right here, x plus 1, y minus 3, and again, you could make those negatives if you want, but if I take this and say that is the opposite of that, negative 6, negative 7, negative 3, then I could figure out that, look, x plus 1 equal negative 6, so x must be negative 7. Y minus 3 equal a negative 7, add 3 to both sides, then y must be a negative 4, and z plus 3 equal 3, so z must be, if you subtract 2, oh, that should be a positive. If you, that's a negative 2. So here we will say, well, look, then the point Q in this case must be a negative 7, negative 4, and a 2. Next up, we just want to make sure that we are comfortable. And again, those I'm going to write in component form. I know that's going to annoy you a bit, but that's how I'm used to it. If we want to subtract two vectors, you put v and you want to put them in order 4, 0, negative 8, and you're going to subtract that from w. W is 6, negative 1, negative 4, and it's fairly simple. You just subtract the components accordingly. 4 minus 6, that's negative 2. 0 minus a negative 1 is plus 1. And negative 8 plus 4 is negative 4. And for part B, so the work here is really reviewing vectors. If you've taken physics, if you've taken trig authentically, that means you would really figure this out quickly. 2u is simply negative 624 minus 7v minus 7 times v, that's 28, 0, and negative 56, minus, now here I'm going to figure this out and then subtract those. So here, we're going to take 8v, that is negative 24, 8, and 16, multiplying this by 8, plus, oh, 8v, not 8u. 8v, there is v, 8v, that would be 32, 0, negative 64, plus u happen to be the very first vector. So here we're looking at negative 6 minus 28, negative 34, 2 minus 0 is 2, and 4 plus 56 is 60, minus, this will be 29, 1, negative 64 plus 2 is negative 62, and if I subtract those, I'll get negative 34 minus 29, what is that, 30, 40, 50, 63, negative 63, and if you take 2 minus 1 will be 1, and if you take 60 plus 62, that will be 122. Let me just double check the math. Oh boy, I see. This was a W. This should have been this. Okay, we're going to fix that. We're going to say that's 2u minus, we're going to make that a v. I'm sorry, I made a mistake, but you get the idea. All right, let me shift things a bit. For what values of t, if any, is the given vector parallel to this? So you want this to be some multiple of this vector. Okay, well, let's see how this works. If I let k equal 2, then that would be a multiple. So in this case, if I let t equal 1, that'll work, because then 2 times this vector will give me that vector. This problem, the same deal. I want to figure out what should I let t equal so that this is a multiple of this. Well, let's see. If I let t equal 1, that wouldn't work. That's negative, that's positive. That's not going to be possible unless I let t equal 0. But this is trivial. The vector 0, 0 is parallel to any vector because we say that's 0 times any vector is 0, and therefore it's a multiple of it. And how about this vector? If I want 1 t squared, well, I want to set that equal to k times 4 negative 1. Let's see. Oh, there's no way. T squared can never equal negative 1, so this is not possible. Well, again, I gotta shift those a bit. I gave it a lot of space. I wasn't sure. Okay, it says find C1, C2, C3 for which the equations are satisfied. Well, look at that again. If you are to write it like this, it will make a lot more sense. Or if you were to write it as IJK, this will make a lot more sense. Well, guess what? If this is the case, then what we're saying here, we're saying that negative C1 plus 2C2 plus C3 must equal a negative 6 because the I component of each must equal the I, the J component in each must equal the J, and of course the K component of each must equal the K. This is how vectors work. So here we have 0C1, the yellow, plus 2C2 minus 2C3 equal a 12. And the green would be 2C1 minus 2C2 plus C3 equal a 4. So pretty much I'm trying to solve this augmented matrix. And we could do that really quick. I could say take twice row 1 plus row 2 in row 2, and I would take row 2 divided by 2, put it back in row 2. I lied. Let's say take 2 row 1 plus row 3 in row 3. And let me write a bit. Take row 2 divided by 2, put it back in row 2. So what would happen? Negative 1, 2, 1, negative 6, 0, 1, negative 1, 6. And if I multiply this by 2, that will become a 0. That will be 4 minus 2, which is 2. That will be 2 plus 1, which is 3. And that will be negative 12, negative 12 plus negative 12, negative 8. And now if I take negative twice row 2 plus row 3 in row 3, I'll be looking at 0. Negative 2 plus 2 is 0. Negative 2 times 1 is 2. That's a 5. And if I multiply this by a negative 2, that's negative 12. That's negative 20. That means C3 equal negative 4. C2 plus 4 equals 6. That means C2 equal 2. And negative C1 plus 2 times C2, which is a 4, plus C3, which is a negative 4, equal a negative 6, it's a negative. So C1 equal 6. So these would be the actual solutions to this. That means this right here is a linear combination of those three vectors. If I could find weights where I multiply one vector by one weight, the other by another, and the third by a third, and get that answer, we say this is a linear combinations of these three vectors. A big deal for what's to come. I need to do a bit more shifting. And here, if I do the same thing, well, obviously, I'm looking at C1. So the I components, basically 1, 1, 2, and a 1, 0, 0, 0, and a negative 2. Oh, oh yeah, that was right. I thought I made a mistake. 0, this has no solution. So basically there's no such weights. So that means this is not a linear combination of those three vectors. That's what that means. And what does it mean when there is a linear combination or not? We talk about linearly dependent and independent later on. That's pretty much it for this section. Let me just shift this up. And there it is.